Coming up on this episode of Here's an Idea.
We're able to take something that would be the size of a refrigerator 10 years ago and smash it into a drone.
We've never flown this fast autonomously.
This summer, my coworker and I found ourselves on the campus of MIT in the middle of a drone testing ground. That's the sound of the Racer AI autonomous aircraft, a sleek X-shaped drone. The sound you hear is coming from the vehicle's 4 propellers, one located on each end of the X. We were quite literally in the middle of the Developers Summit for the Alpha Pilot Innovation Challenge. Sponsored by Lockheed Martin, Alpha Pilot challenged 9 teams to create software that could guide a drone around a course autonomously. No pilot. Now was the chance for each of the teams to test out their code. The indoor facility at MIT was a big, echoey room with high ceilings. A few people were moving back and forth with walkie-talkies around 4 square obstacles. These gates looked like giant 10-foot picture frames, neatly fixed around the space in an almost full circle. I caught one of the guys with the walkie-talkies, James.
So here we've set up 4 2-scale AI robotic racing gates, and teams have the chance for the first time to take their autonomous solutions, deploy them to a drone, and gather data inputs from the drone to kind of give validation to how well their solution is performing in simulation and then how it'll perform in real life.
James was speaking quickly. After all, there was a lot of work to be done, and who wants to talk to a guy doing a podcast when you can test out a drone that flies 70 miles an hour on its own in a second and a half? On this day, each of the teams had 90 minutes to test out their algorithms and to learn what worked in their simulations versus what worked here in reality at MIT. But really, with those 90 minutes, they could do, well, whatever.
Whatever scenario they want, whatever's most useful. So some teams will just very slowly go through, some teams will circle one kind of element.
The task for a lot of teams on this particular day was to have the drone, as autonomously as possible, take off, hang a right turn, and then fly in an almost complete circle, passing through the openings of these 4 picture frame gates along the way. During most of the testing, the drones were controlled by human pilots. After all, these machines are expensive, and when you're learning about any new piece of hardware, it's important to take it out for a test drive, as safely as possible. But the idea is that these drones will ultimately be autonomous. They will fly through a course guided by each team's software, which until now had only been tested against simulations provided by the Alpha Pilot sponsor, Lockheed Martin. As James said, the teams could do what they wanted with their time on the course. For those 90 minutes, some teams go slowly through. Other teams have their aircraft do a backflip.
During our tests today, we had the pilot do some flips and we asked him to do basically as aggressive as you can, as long as you feel comfortable. So he's like, okay. And I think everyone's heart stopped a little bit when he did. He almost crashed, but keyword almost.
This is Manan. We caught him later in the day in his workroom upstairs from the MIT testing ground. He had just tested the drone and its software out on the course. Manan Gandhi is a captain of one of the 9 teams competing in the Alpha Pilot Challenge, and he told us about how his team's pilot had decided to dedicate a little bit of his precious testing time to some mild drone acrobatics.
Yeah, so you saw the 3 gates, and so I believe it was gate 3 where he passed through it fairly quickly, pitched back, so the quad rotor went fairly far up, did a flip, and then landed feet first on the ground, all within less than a second. There should be some cool first-person video of it somewhere.
Each of the 9 teams has been given the same hardware, the same simulator setup from Lockheed Martin, and it's up to machine learning pros like Manan to create the software.
We're all developing our own artificial intelligence. We're all developing on the same hardware, but today is the first day we actually get to touch the hardware and experience all the joy that comes with that.
Yeah. So when you say joy, what brings you joy when you're testing this out?
Oh, I mean, it's really cool to see it fly. I mean, everyone's a little kid at heart.
In this episode, we take you through the highs and lows of the Developer Summit and talk to some of the engineers who are writing the code and designing the hardware to send drones through obstacle courses without a pilot. These autonomous drones will compete in what's known as the Drone Racing League, or DRL. The winners, in fact, get $1 million in cash and an additional $250,000 if they beat a human. We also speak with a lieutenant colonel from DARPA who's leading a competition of his own, a kind of digital dogfight. A fast pilotless aircraft has the chance to impact our everyday lives in ways that are both exciting and even frightening. We'll talk to the people behind these competitions about why they matter and why racing drones is more than just mere entertainment. So, here's an idea. AI in the air.
We have a floor dedicated to motion capture. We have a full EE laboratory. We have a manufacturing drone studio in the back. I think in these 3 floors there are well over 2,000 drones. We build, solder, test, everything. We have fume extractors that run outside.
This is Ryan Gurry. He is CTO of the Drone Racing League, or DRL. We spoke with Ryan at the DRL headquarters, which are 3 separate floors in a rather long but narrow office building in the Flatiron district of Manhattan. Not necessarily the kind of environment you'd expect to host a drone racing league.
We have not yet flown a drone from a floor to a floor, but one day we hope to.
DRL is basically a technology company wrapped in a media and entertainment company. They build drones and then race them on TV. Now in its 4th season, the DRL Alliance Championship Series allows pilots to race in what's known as first-person view, or FPV. With FPV, the drone's camera offers a pilot-like perspective so the aircraft can be remote controlled.
FPV is crazy. You wear a video screen and you control a small racing machine that has absolute instant acceleration and can maneuver in any direction, right? And when you get good at it, it's just like flight. You forget that you're on the craft. You forget that you're on the ground. You think that you're actually on the craft. And I love motorsport, and I ride a motorcycle. I love the feeling of speed. And when you're flying FPV, there's nothing faster or greater than that. It's a huge rush. It's super fast, and you can't get hurt. So you can take all kinds of ridiculous risks while you're flying.
And in the DRL Championship Series, these pilots are racing identical, custom-built drones at speeds above 80 miles an hour through 3-dimensional courses in fun, visually appealing landscapes.
We put on large, multi-mile-long 3D courses. We create the technology that fosters these races. So we develop our own radios that go far away. We develop our own drones, our own diagnostics and operations.
The entire goal of the Drone Racing League, says Ryan, is to create a racing environment where there's meaningful competition, where you can follow drone racing and have actual winners and losers. Founded in 2015, the league has since developed numerous sponsorship and media agreements. You may have even caught them on NBC.
And it's Duncan in right, first along the western run. He'll now make that right turn. This is the first switchback, the Swatch gate to the square gate. Duncan being very aggressive, pushing out ahead of the pack as fast as possible.
A new undercard in these races now, however, is the AIRR, or Artificial Intelligence Robotic Racing Circuit, where the pilot is replaced with software.
So right now we're working on AIR, the Artificial Intelligence Robotic Racing Circuit. More or less that's creating, a platform for artificial intelligence developers to be able to produce the greatest autonomous drones on Earth.
The teams in the Alpha Pilot Challenge, teams like Manan Gandhi's, who met at MIT this summer, are the artificial intelligence developers Ryan is referring to. The teams will deploy their code on the just-released Racer AI aircraft, a unique vehicle. Racer AI's propellers are on the underside of the drone, and they spin in the opposite direction, pushing air downward. 2 pairs of cameras, or 4 eyes really, are mounted on the carbon fiber frame above the propellers. The stereoscopic cameras create a field of view larger than a human's, about 130 degrees. The drone has an inertial measurement unit to measure accelerations, a gyroscope to measure rotations, a processor, and a laser rangefinder to detect the distance of objects. And it looks pretty cool.
In the front of the drone is this large obtuse angle, so it looks like, a flying crossbow. And, it weighs a lot more than a DRL racer. It can generate, I think, 16 to 20 pounds of thrust, and it uses 9-inch propellers compared to 6 or 7, which is what we use. It has a canopy. It looks like a Batmobile. It has a large red triangle as its eye.
Before getting a look at the part crossbow, part Batmobile drone, however, Alpha Pilot participants first had to deploy their code in a simulated environment, the one provided by Lockheed Martin and DRL. Not until their preliminary test at MIT did they finally get a chance to put their SD card on the Racer AI and have it take off. But you want to get a few things figured out before you hit go. You need to understand the properties of the vehicle and see it up close. Back at the summit at MIT, Manan got to finally handle the drone for the first time, in real life. It was heavy. After all, it had to hold a battery and a dense processor. Manan needed to figure out the difference between the reality of the MIT course and the simulated course he'd been practicing on. The lighting in MIT's course may be different than the lighting given in the simulation. The teams at the developer summit that day needed to get some real baseline data.
You want to collect camera images of the drone flying around, so from first-person view. You want to collect acceleration data, gyroscope data, laser rangefinder data. They have a fantastic motion capture system set up for us, so we have the position of the drone, the orientation, all of that recorded and given out to all the teams. So then we can learn as much as we can about the hardware.
The simulated courses provided by DRL featured the gates. Teams were given a couple months to practice and get their code working. The teams needed to create software that could spot those course gates, the picture frame looking squares, and go through them as quickly as possible. They could test out their software from their desks before loading it onto the Racer AI aircraft and seeing how their code matched up to the real world.
It's so tough. It's so tough to model accurately in a simulation that no matter how good of a simulation you might have developed, the real world is so much more diverse and challenging, and there's no way to replicate that exactly in a simulation.
This is Chelsea Sabo. She's the technical lead for Alpha Pilot. Chelsea works for Lockheed Martin and has been guiding the Alpha Pilot teams as they test a drone's capabilities, backflips and all. Before Chelsea arrived at Lockheed, she studied autonomy in small UAVs. Now she does a lot of drone work.
It's my area of expertise. It's what I like and get excited about. So, mostly drones, a lot of vision-based navigation, again, all around intelligence, robustness. And then I do a fair amount of collaborative autonomy. So how can our drones work together to accomplish tasks more effectively?
Part of that collaborative autonomy involves speed. Teams may be able to get their drones to spot objects and gates at casual speeds, but what about at 70 miles an hour?
We've never flown this fast autonomously, right? This will be one of the first times. And so we're getting pretty good at flying really slow and doing that visual processing. We're getting better. The tricky part is going to be going fast. So what you'll learn by doing those crazy maneuvers is, what does my camera imagery even look like when I do those crazy maneuvers? We don't fully know. So that's kind of what they're hoping to tease out. Like, where am I getting motion blur? Am I getting glare? How much glare? How much do I have to accommodate for? Those sort of things.
Manan agrees that one of the toughest challenges is getting the vision right. At high speeds, there's a reality that can't always be found in simulation. When you go as fast as a car on the freeway in under a second, the image quality changes.
I think the hardest part is localizing yourself and basically navigating that course when moving at very high speeds. Your camera is going to start blurring. You have less time to react if there's going to be an obstacle in the way. And in general, at high speed, the dynamics of such a vehicle change.
Manan Gandhi is a PhD student at Georgia Tech. His team is made up of 5 undergrad students, 4 graduate students, and an advisor. Manam's expertise is machine learning and pattern recognition. He studies how to turn data into specific, smart commands for a given technology, whether it's a robot, a car, or a drone.
You have data you've collected. Could be data from rain, data from temperature, data from images, and you want to extract a pattern out of it. You want to see, is there structure in this? So then you can train something, you can train an algorithm to do that for you. And so when does this become intelligent? Well, this becomes intelligent when you start thinking about, all right, well, if I can collect data and I can find a structure, then maybe I can start making decisions on my own based off of what I've seen. A good example of that is that I have my iPhone app, and when it sees my face, it's going to turn it into a dog. Things like that, where it recognizes that everything in the field is not a human face, and when it sees a human face, it'll put puppy ears on it and make you laugh. And so there's this line between machine learning and artificial intelligence comes into how do I inform my decision maker, the artificial intelligence, by finding patterns in what I see, which is machine learning.
With this kind of appreciation for patterns in machine learning, teams need to take the image data, sensory data, and vehicle data, and then use that information to initiate commands with the drone.
We have to build together the logic for how do we make decisions. We have to build together the entire estimation pipeline from images to sensory data to our vehicle position. And then we have to put together our control solution of, okay, how do we take where we think we are, where we think we need to be, and tell the drone this is the motor velocities that you need to input to go there.
With such a difficult task to accomplish, the mood at the summit is a bit all over the place, says Chelsea. There's excitement when a drone does what's expected, disappointment and frustration when code doesn't execute.
Probably changes every 5 minutes. You know, it's like you're excited, you see the drone, you can't wait to see it fly. Anxious, you know, and then you're like, oh God, my code has to work tomorrow, right? So, and then I have to make sure all our stuff works for tomorrow. So there's a lot of pressure on everybody. So you go through the cycles, you get excited, then you go, oh gosh, I gotta make it work. Then you get in the lab and you're like, oh, please work.
For Manon, competitions like this are just as much an exercise in innovation as they are in patience.
You really hope it's gonna work. You know it works on your home computer, but when you bring it out to the drone, something's gonna fail. That's hardware. That's just the nature of it. And that's something that we expect to happen, but you're always gonna be a little bit sad when something doesn't work how you want it to work. And so those are things you overcome.
When it comes to competitions of artificial intelligence, the Drone Racing League isn't the only game in town. Some of the biggest names in tech are out trying to pit the fastest AI aircraft against the most skilled human pilots. In November of 2017, NASA researchers at the agency's Jet Propulsion Laboratory in Pasadena, California, held a time trial, sponsored by Google, between an autonomous aircraft and world-class drone pilot Ken Liu. The course forced the drones, powered by Google's computing platform, to twist and turn through a half-dozen scattered arches on the ground, lap by lap. The drone lost to Ken Liu. For the official laps, Liu averaged 11.1 seconds, compared to the autonomous drones, which averaged 13.9 seconds. At the time, JPL researcher Rob Reed said the autonomous drones can fly much faster, and that one day you might see them racing professionally. We reached out to NASA, who hesitated to comment on another company's work, considering the drones used Google's computing platform. Similarly, NASA did not want to talk about DRL's technology. But NASA has led plenty of efforts in automation, whether it's building autonomous robots to compete in search and rescue tasks, creating software to guide its rover to rocks of interest on Mars, or developing software that automatically tasks a spacecraft to take photos when an event of scientific interest is detected. We also reached out to DARPA, who's been working hard at developing advanced autonomous algorithms for aircraft, as well as search and rescue robots. DARPA has a new effort to advance AI technologies for autonomous flight, Air Combat Evolution, or ACE. Why ACE exactly?
Like a lot of DARPA programs, I start with the acronym I want first and then come up with everything else later because I wanted it to say ACE.
This is the guy who's in charge of ACE, and he's somebody who knows not to settle when it comes to names.
My name is Dan Jaworczyk. I go by Animal, and I'm a program manager in the Strategic Technology Office at DARPA.
As part of his work with ACE, Dan Animal Jaworczyk is leading a competition called the Alpha Dogfight Trials, which will pit AI algorithms against each other, a kind of digital dogfight.
The Air Combat Evolution program is about taking these sorts of autonomous algorithm systems and putting them into air combat environments in a way that allows us to build trust in these particular kinds of algorithms.
The competition that Dan is leading is one that exists entirely in simulation. In the Alpha Dogfight trials, participants develop algorithms capable of controlling a simulated blue aircraft, such that it can defeat a simulated red aircraft by performing basic fighting maneuvers, like maintaining a secure position or locking in on an opponent. The challenge begins with an open-source video game. Then teams create an AI agent that plays the video game in a head-to-head autonomous fashion. Each team plugs their thumb drive of code into a computer, the thumb drives load the agents, and the agents play each other. From there, really, they push play.
My hope is that this kind of competition style would give rise to a very rapid expansion in performance of these algorithms.
The 8 teams are a mix of universities and industry. Large companies like Lockheed Martin, small companies like SoarTech in New Jersey, and student engineers from Georgia Tech. Some of the main names from the Drone Racing League competition.
The artificial intelligence ecosystem is quite broad and deep, right? There are a lot of different folks that are doing great work, all the way from universities to the kind of classic industrial base, with small business somewhere in between there. And part of the reason for why we did the Alpha Dogfight trials was to gain access into them.
The need to dogfight or to maneuver the plane to a position of advantage was important in World War II, when fighter planes had guns only in the front of the planes and there was no modern system to identify targets. A fighter had to skillfully find ways to bring down an opponent at close range. Even though the days of dogfighting may be over, Lieutenant Colonel Javorcik considers the one-on-one Top Gun-style competition to be just the right kind of task to test out autonomy.
It's kind of an entry gate that introduces them to a very dynamic environment that requires them to make decisions very quickly, but that isn't burdened with a lot of additional information like complicated sensors, think radars and other types of sensors that can cause the decisions to be more complicated.
In other words, the challenge is kept simple. The objective, maintain a position consistently behind the opponent to maintain what's known as the control zone. And the simplicity of the task, in a way, demonstrates the complexity of the AI-powered aircraft challenge. It's important to remember that aircraft isn't as autonomous as you might think. We have a long way to go.
People seem to think that when we see something on the news and it's talking about a drone, that's some unmanned thing that's autonomously flying, or that there's one human being that's on the ground and controlling multiple autonomous systems. And the opposite that really could not be farther from the truth.
Typically, an unmanned aircraft has dedicated personnel for each aspect of flight: the vehicle maneuvers, the sensor operation, the maintaining of the communications link, and the handling of launch and recovery. Each part has its own team. It'll be a while before aircraft is fully autonomous, but not because of technical limitations.
Really, it turns out that the manpower footprint that's required to operate an unmanned aerial vehicle today is quite high, on the order of 10 or so people. And when you start looking at the manpower requirement there, you start to recognize that we are in an area that is in bad need of autonomy. And it's not for technological limitations. Most of that is because we don't really trust the systems to work the way that they could.
Programs like ACE are trying to build that trust. It's easier to trust autonomy when there's less at stake. But autonomous drones will be part of high-stakes operations, and they need to be right all the time. Here's Ryan from DRL again.
They can't fail. Even if you fly a drone and you crash it, you have a human to blame. I don't think there's any forgiving nature about robots failing. So I think in order for autonomous systems to succeed, they have to be almost perfect.
There are a lot of challenges that are unique to the combat environment, or to air combat in general. The consequences if AI fails in these scenarios are tragic ones. And to Dan Javorcik, nothing captures those consequences quite like the pilot operating handbooks, known as Dash 1s.
We say that a lot of the lines of the Dash 1s are written in blood because somebody made a mistake or it was not articulated well, and they paid a pretty high consequence as a result of that.
Engineers need to build a trustworthy system, one that has to start with the low stakes of simulation. Ultimately, the goal of the ACE program is to usher in an eventual teaming between the human and the machine. Before there's collaboration, there needs to be some competition.
In the Alpha Dogfight trials, we are doing it in simulation only. In the broader ACE program, we are doing effectively the same thing, but in live aircraft. And building trust in that final state is a much more daunting task for this program and for these algorithms than simply getting it to play the video game. Once you've built a system that appears to work and appears to be trustworthy, now we have an opportunity to pair that up with human beings so that we can actually take it to this more collaborative type of manned-unmanned teaming scenario that we would like to eventually get to.
What does that collaboration look like exactly? Animal was an F-16 pilot, someone who has experience in the challenge of multitasking while flying thousands of feet in the air.
If we have autonomy that's able to handle a lot of these lower-level tasks and can slowly get better at handling the more complicated ones, we preserve the limited cognitive resources that we have to handle these really challenging scenarios, right? And so when it comes to, say, combat search and rescue, if I have an environment that is threatened, if the autonomy is able to handle automatically a lot of the basic flying tasks or even some of the basic threat reactions, I, as the human battle manager, can think at a level that allows me to maybe do longer range planning for how to recover the downed aircrew or whatever is the actual mission for that day.
So on October 8th of 2019, the Drone Racing League kicked off its first ever autonomous competitions. 9 teams were given 3 chances to move on their own through a track featuring 4 square-shaped checkpoints. The square gates were arranged in a row. Despite the simplicity of the straightforward track, DRL's launch of the autonomous racing circuit was marked by ups and downs. Specifically, 5 of the drones stayed up, and 22 out of the 27 flight attempts went down. The event was held at an arena at the University of Central Florida, in front of about 500 fans. A majority of the aircraft missed the first checkpoint. Some drones veered into walls or crashed into the ground. But despite the low success rate, let's be careful not to call the event a failure. Representatives of DRL say this is all part of the process. After all, this kind of competition has never been done before. Reporters for the Orlando Sentinel were on the ground that day. They spoke to Fraser Kitchell, one of the team leads. Fraser told the paper, "We'll probably crash a lot more before we're done." Fraser's team, KEF Robotics, did not get through the first gate that day. Neither did Manon's, by the way. On the day of the race, DRL hosted a panel that featured MIT professor Surtak Karaman. Karaman said that if you're not seeing a drone go down, you're not pushing the technology enough. And the autonomous drone racing teams will have additional chances to dust off their drones and try again. This was just the first race of 4 this year. Each team, learning from their mistakes, will have their chances to get better and better, getting closer and closer, perhaps, to the capabilities of human pilots. We asked Chelsea if an autonomous drone would be able to beat a piloted one. She wasn't so sure.
I don't think the autonomy is beating the human this year. If I'm being very frank, we are a ways off of that. This is such a hard problem. Again, and humans are so good at so many things.
Things like vision. If you walked into your house and closed your eyes, you would know where the kitchen is, the stairwell, the bedrooms. A computer, at least for now, needs more time than that.
Right now, a computer is going to take, 10 seconds to understand the room. It's going to take another 10 seconds to understand what is the best trajectory to fly in, and it's going to take another 20 seconds to actually fly there.
There's so many things that we're tracking and taking in, and that being able to abstract what's important and that information compression we're so effective at it. We haven't quite really nailed that with our drones yet.
But we're really at a tipping point for a lot of different technologies working together, says Ryan. The technologies are improving. Even the Racer AI is heavy because it carries a load of sophisticated equipment, like a multi-core processor. The drone has an inertial measurement unit that can sample 1,000 times a second, understand the angle of the craft, and make adjustments.
It's basically a massive computer jammed into a small size, and all it's doing is running Photoshop filters. It's perfect for computer vision. And, we're able to take something that would be the size of a refrigerator 10 years ago and smash it into a drone and, in this case, try and contend with humans.
The technology is starting to give the human pilots a run for their money. Algorithms called neural nets work much like a brain. The neural nets can classify data within datasets, recognize patterns, and then make decisions based on that data. An autonomous car, for example, can infer its own rules with a neural net, avoiding obstacles like a ball in the street, based on learned examples. There's also something called simultaneous localization and mapping, or SLAM. SLAM uses sensory data to create and update a map of an unknown environment. If you combine neural nets and SLAM with a drone, there are all kinds of possibilities.
I think that, when you start to combine all these things, you start to get something truly powerful. Supercomputing, really awesome sensors, and amazing software that utilize modern, algorithms. I think the next 20 years are going to be remarkable in terms of what we're going to see. SLAM is going to happen just as fast as a human. You're going to be able to use neural nets to see how far away things will be. You're going to be able to fly proficiently and have pathfinding happen rather accurately. We're going to see drones, surpass human capabilities, and go far beyond what they're currently able to do.
Manan agrees. He believes the work being done in the Alpha Pilot Challenge is the beginning of an exciting path for autonomous aircraft, one with all kinds of applications and possibilities.
This is where automation really takes off. You think about disaster relief, where you can't assume that you're going to have very good sensor information, but you can send out quads to look for survivors. You think about agriculture, where you have acres and acres of fields of crops that you can inspect visually using these autonomous drones. Really, the technology can be applied in many, many areas that we haven't even thought of, because, again, there's such a big creativity aspect of this. Once the AI stack is theirs, you can really imagine what you can do with this. And so hopefully it'll be beneficial to as many people as possible. And we see the value of it, and we want to try to bring that value to as many people as possible.
Maybe it'll feel odd to someday jump into a car and have it take you to the store without you having to actually drive. But the gap is narrowing between humans and automated technology. And these kinds of scenarios, including a drone looking after a farmer's land, is something we might have to get used to. Ryan says there's going to be a time where we'll have to trust in robotic elements that can perform greater than a person.
There's going to be these the moments in time where things start to shift, and I think a drone navigating a 3D space by itself is going to be a pretty serious measurement, especially when it can do that at faster than a human, or at a really high level performance. Right, that's going to be a pretty big yardstick. In the future, everything that we interact with will have cameras, and it'll be able to maneuver in 3D space and operate better than we will.
In other words, the real competition might not be between drones, but between AI and us, the humans. Let the games begin. This has been an episode of Here's an Idea. This episode was written and produced by me, Billy Hurley, Kendra Smith, and Peter Bonavita. For more information about the technologies featured in today's podcast, you can visit our episode page at techbriefs.com/podcasts. Our podcast page also gives you an opportunity to subscribe to our Here's an Idea newsletter, which provides photos, facts, and follow-ups on the technologies and technology creators featured in each episode. And we want to hear from you. Give us a review on Apple Podcasts and send us feedback to podcasts@techbriefs.com.